My name is Dean Wampler. This is kind of my experiences with using Spark, and not just my experiences, but what a lot of us have learned about strengths and weaknesses of the JVM and Scala. I always put my photography in these things, so if you're bored with the content, you can at least look at pretty pictures, or hopefully. This is actually Olympic National Park, which is in the northwest corner of the continental US, west of Seattle and southwest of British Columbia, or Vancouver in British Columbia, Canada. Okay, you can actually get this talk, and actually there's a longer version of this talk at my vanity website, polyglotprogramming.com, and of course it'll be on the conference site as well. And obviously I work for Lightbend. It's my job to figure out what we should do with Spark and other big data tools. As many of you may know, a lot of the big data tools adopted Spark as their core language, like Spark, adopted Scala rather, like Spark and Kafka, and it's actually driving adoption of Scala right now, which is kind of cool. So first, let me briefly talk about Spark. So how many of you have actually used Spark? Okay, great, most of you. So I'll go through this fairly quickly because this should be mostly review, but just to give you a sense of it for those of you that have never dealt with it before. This is areas famous for rainforests, which is and really big trees. So it's basically a distributed computing engine for the JVM. It's designed for data-centric computation, where you write a job, and as you'll see, the abstractions look just like the Scala collections, at least if you're using the Scala API, and yet it's actually distributed over a cluster, so you can work with terabytes to petabytes of data with reasonable performance, as long as your cluster is big enough. Instead of vectors and lists and things like that we typically work with, there's this thing they call it a resilient distributed data set, which is a collection that's partitioned over the cluster. And so it runs in parallel when it's processing each of these partitions. And it's resilient in the sense that it's actually computing the graph of processing steps that you've defined. So if it loses a node, or another way, loses a partition, it can go back and reconstruct it. So that's where the resilient comes in. And it actually not only supports Scala and a Java API, but because data scientists tend to still prefer Python and R, despite the arguments that Andy Petrella and I made yesterday, it also supports Python and R, or SQL. And we'll see quick examples of that as well. And importantly for all of us that are, I mean, this is like table stakes now for most of us, but being able to work interactively with code is really nice, but it's also very important when you're doing interactive exploration of data. And if you've ever used like a SQL environment to look at data that you've got in a database, it's the same experience. It's really crucial not to have to write and compile and run a program every time you want to do a query or some other interactive step. And because of these REPL properties, it supports these nice user interfaces called notebooks, where this is actually a screenshot from one we went through in my talk yesterday, where you can intermix like markdown documentation, actual code that's run in the REPL. You can graph results and all that kind of stuff. And there's several of them out there now. This happened to be Spark Notebook, which is Java-centric, but Jupyter is one of the sort of pioneers, maybe not quite a pioneer, but one of the more popular ones that was based on Python. All right, so with that, let's look at an example. It's one of my favorite ones because it really shows how concise you can make code and yet do something non-trivial in Spark, and it's the inverted index. This is sort of what you would do first if you wanted to build a search engine. Suppose you have like a corpus of documents or something like the internet or the World Wide Web, and you want to index it so that you start with, say, a reference to a location and then the contents, and invert it so that you end up with an index of all the words that are found at each place, and then a list of locations and counts. So the counts are important because obviously, if I'm searching for the word like Spark, I'd like to find the pages on the internet that really talk about Spark, not just mention it in passing. So counts are a good measure of relevance, approximate measure. And this is the whole program, the entire thing that you might write in the REPL using Scala. And I'll actually go through this, blow it up a little bit so you can read it. But it's kind of cool that you can put a whole thing on a slide. Actually, I'll come back to that in a little bit. But first, let me just talk about the structure of it. Let me back up one thing. So I chose the color scheme specifically to emphasize that functional transformations are really the key here. So they're in red. So all the red stuff are things that are doing common operations like mapping, flat mapping, filtering. Reduce by key is like an optimized group by, which hopefully group by is familiar from SQL, and so forth. So you have these nodes of processing that you're defining. I've sort of captured them schematically on the right. And once you understand all of these little tools in your toolbox, like for Scala collections, then you can crank this stuff out really quickly. So the first time I wrote this example, it took me maybe 30 minutes to write it because I knew all of those steps. And you get experience decomposing a problem into a sequence of steps, and then you can crank stuff out quickly and not get caught up in the boilerplate of more verbose Java or whatever. But what's actually happening is you're defining a data flow of steps, a directed acyclic graph to be specific. This is linear, but I could easily have sort of branching and joining of data. It's lazily defined, so nothing actually happens until I say, give me some results, in this case, right back to the my file system, and then it actually figures out how to run this across your cluster. But the API looks very much like the Scala API in terms of I'm passing anonymous functions to map and filter and so forth. So that's really nice. The other thing it does, it tries to be very performant. So rather than generating, I said we could be doing like petabytes of data, right? And I wouldn't want to instantiate a new petabyte collection on each one of those steps. These are immutable objects, these RDDs. But it doesn't do that. It actually only materializes things at the end of stages, so-called. And what's a stage? Well, when I'm doing mapping and filtering and flat mapping, that kind of stuff, I can work in isolation with each partition. I don't have to get data between partitions if I'm just mapping over each record. But if I do something like a group by or a join, then I have to bring together things that share the same key, and that triggers a new stage, as they call it. But all of the things that are still bright, those are the things where I'm going to materialize some result. In the intermediate case, I'll write some temporary files, and then those will be sucked over the cluster to the appropriate nodes. Or I'll produce my final output in some sense. So it's fairly efficient about taking that graph of processing and synthesizing relatively efficient JVM code that you're going to actually run. And once you have a good core like this, then you can layer on top some powerful higher level APIs like SQL. So you can actually, if you think of, I always like to think of SQL as like a restricted functional programming language. It's, based on set theory, roughly speaking. We don't have anonymous functions and all that kind of stuff. Maybe we have user-defined functions which sort of fake the same thing. But it gives us the idea that we can declaratively state what we want in terms of what kind of data we want to see, what transforms we want to perform, or data we want to create, and then let the runtime optimize how that's actually computed. And really all of the performance optimizations that have been happening in Spark, many of which I'll talk about in this talk, are happening in the context of optimizing SQL. The other advantage for doing it that way versus at the RDD level is that SQL is a more constrained problem. You're not trying to solve, boil the ocean or whatever metaphor you want to use. You're trying to solve a more narrow problem, and that makes it easier to optimize. Data frames, this is a word from the actual name of the class you use is called a data frame, but this API is inspired by a Python API called data frames, which is actually a copy of a R language API called data frames, and that's where the name comes from. But I like to think of it basically as just SQL. And this is what it would look like if you wanted to actually write this. Let's see, I think I'm drilling into this. Yeah, here we go. Okay, so I start off by creating a Spark context. That's how you always enter your program. It knows, like the master argument here is where the cluster is and things like that. And then you wrap that in this thing called a SQL context that brings in this SQL abstraction or data frame abstraction. And then there's some nice facilities where if I'm storing data in what happens to be a very popular format called Parquet, it gives you column storage and compression and some other advantages. Then I can just say, all right, I want to read this Parquet data, and the schema is carried with it, so I know exactly what the records are. And I'm actually loading, this is the data that you can get off the internet. It's actually all the public, or rather commercial flights in North America from like 2000. Actually, I think it goes back to 1985, in fact. But anyway, it's kind of a fun data set to play with. So I'm going to load the actual flights, the actual planes, like the tail number of each, 747 or whatever that's out there. And I'm going to register these as temporary tables in sort of the same way I might do with SQL. And caching this is where the abstraction leaks. I need to tell Spark, look, keep this data in memory and don't just keep going back to the hard disk to get it, because I'm going to keep going over and over this data. And then I can embed SQL queries if I want, like this. I mean, this is stringly type programming, which we're told is evil, right? But it's actually really great when you're just doing interactive stuff, because you'll know right away if you screwed up the query. Or, well, actually, what am I doing here? I'm actually joining the flight data and the plane data on the tail number and then limiting to the first 100. So I get more metadata, let's say, about the airplane that actually did this flight. But I could also do this with this programmatic API that's a little bit more type safe, but there are some issues with it that aren't perfect from our point of view as Scala developers. But nevertheless, it's a way that's a little bit safer than just stringly typed SQL queries. Now, there's something interesting about this expression at the bottom, and I blow it up on the next slide. So notice what I did. I did flights, join planes, that you could think of what the equivalent SQL would be. And the join criteria is take the column that's the tail number in flights, and I want those to be equal to the column or tail number in the planes data set. And notice the triple equals. This sort of looks like an anonymous function, which is what we're used to with things like map and flat map and all that. But it's actually a mini DSL for expressing this concept that it turns into an abstract syntax tree at the Spark level. And so now they know exactly what I'm doing, and they can do optimizations based on this expression. Whereas if these were anonymous functions that I was passing, the ones that we're used to every day, that becomes completely opaque to the library like Spark. So Spark can't do any optimizations if this were anonymous functions. But because of this little mini DSL that's constructing an object that represents the join criteria, it can actually do some aggressive optimizations about how this will be run when I actually do this query. So that turns out to be pretty important. And it turns out when they introduced this new data frame, SQL API, this is what happened with the performance numbers. The blue is the previous results for the RDD API. And notice that Python was significantly slower than Scala. Even though Python and R are actually getting translated into bytecode immediately, there was enough overhead that it kind of sucked. But you know, maybe not too bad. If you were a data scientist, knew Python, and didn't want to switch to Scala, you know, maybe it was okay. But notice what happened when they introduced data frames. Suddenly the performance became equivalent. There's still some small issues in performance, but the reason is because they more aggressively get to bytecode and they're doing a bunch of optimizations we'll discuss. So that's where they get like the doubling of performance right here, but then also for Python it becomes equivalent to Scala performance. This was kind of a breakthrough really in big data. You know, if you go back to the bad old days of its predecessor MapReduce, your data scientists might model stuff in R or Python or whatever, and then they would toss their models over a partition to a bunch of Java developers and pray that they actually translated it to Java correctly and didn't make mistakes. Really horrible way to work. But now in principle, you could just deploy these Python models or whatever it is you're building, and it would just work and give you excellent performance. The numbers are actually far better. Like the release of Spark that's coming out this summer is dropping this by like a factor of 10, 10 better. And we'll see why as we get to it here in a few minutes. This is just a laundry list of the functions on this data frame object that represents the SQL queries that you're writing. And if you just scan a few of the yellow names, you'll see things that should be familiar from SQL, like group by and select and all that, because basically it's an abstraction around the relational model. Now, the other thing that they introduced was a way of doing streaming, and stream processing happens to be the other new hotness right now. Like, if you've heard of Kafka, it's on a rocket ship the way Spark was 2 years ago. But it turns out Spark started out as a batch mode system where I'd have all my data somewhere, and I'd run this big job that would just stream, go through it all. Stream's the wrong word. And do some processing and then finish. But when streaming got popular, they came up with a clever hack. They said, well, actually, this is a batch system, but it's pretty efficient. So what if we just captured data in time increments, like down to a second or so, and then ran a little batch job over each of those intervals? And that's what this really is. So dstream is discretized stream. This is actually going away eventually because it turns out there are a lot of limitations that true streaming engines support that they can't. But nevertheless, it gives us ability to do like very sophisticated stuff where I don't need sub-second latency, I can maybe take 10 seconds or a second to do something, but I don't want to wait hours or whatever until the next big batch job kicks off. And so basically what happens is for each of these time intervals, you'll capture whatever events came in, like over a socket or from Kafka or whatever, and stuff those into an RDD, and then do whatever job you want over the RDD. If you've ever used the Lambda architecture, where you combine like a streaming engine and a batch engine, and then try to join the results together, this solves that design problem pretty nicely, because you can have one tool that you write your logic in, and then whether you wrap it in a stream or wrap it in a batch job determines how it's executed. But you're not implementing the same logic twice in different tools for those different kinds of compute models. And then just for completeness, there's two other higher level libraries. One is a machine learning library called MLlib that the best part about it really is it's got some low-level primitives like a good linear algebra library, but it's not a very comprehensive set of higher-level algorithms that you find in machine learning. And I think they're evolving towards a model of just providing the primitives and then letting third parties provide the custom libraries like deep learning, neural networks, random forests, stuff like that, if you've heard of those things. And also there's a graph library, the idea being that if I have data that nicely fits a graph, like here's an example of PageRank from Wikipedia, your social network on LinkedIn or Twitter are also examples, then you could represent that data as a graph and use graph algorithms, nearest neighbors, connected components, and that kind of stuff to compute it. But that's all I'm going to say about those. This is my favorite photo, actually, from this whole thing. This green thing is a rope that's about this big around. It's one of those ropes you use to tie ships to docks. Unfortunately, this beach was covered in detritus, and it was mostly debris from Japanese fishing vessels after the tsunami, that was, in 2011? But anyway, so there's this big rope, and then one of my hiking partners there in the middle. So, but anyway, now we've got this sort of background about what Spark is all about. Let's go down and see, what does it mean in terms of using the JVM for all this? Well, of course, the JVM was picked for all of these tools because, we just had a lot of experience running very big JVMs, running lots of them. The DevOps problem was sort of solved mostly. We just knew how to run this stuff, so it was a good platform. And we could get a lot of Java developers, too, if that's the kind of people we wanted to hire, right? And we've got a ton of tools. We now have several languages, not just Scala, but Clojure, which is mostly invisible, unfortunately, in this space. I'd kind of like to see more of it. And then a lot of libraries. And here's some of my favorite Scala-based libraries. Akka, of course, that you probably know about. Breeze is a linear algebra library, and so forth. I won't go through all of them. And developer tools like Eclipse and IntelliJ. And because of this, we've had this big ecosystem emerge on the JVM, including some Scala-based libraries, the ones at the top in Kafka, and Hadoop, which is sort of the gold standard in a way for big data databases. I could have put easily double or triple the number of icons on this slide. However, there are some imperfections. There's some things that have caused problems for us, and I want to talk about that next. Well, one of the practical issues is that if you're doing data science, there are just a lot more libraries available in the Python and R communities for complex statistics, machine learning models, and so forth. We're catching up in Scala, but it's probably going to be a long time before there's any sort of parity. Garbage collection turns out to be a major problem in these big data computations, and let's actually explore that a little bit. Well, it turns out that most of the time when you're doing big data stuff, you're typically running heaps that are 10 to hundreds of gigabytes in size. And as some of you may know, you can now get 2 terabytes of RAM on single instances on Amazon. So that's just going to push these numbers higher. Because when you have terabytes to petabytes of data, you have very little memory taken by your code, and most of it is just storing data. But this is not a very common size for heaps for the kind of microservices or whatever buzzword you want to use, the sort of things we've been writing for years outside of the big data world. So it's kind of new territory, and we're pushing the limits of what's possible. And it turns out that typically the way RDDs and data frames are used, especially if you start caching them, is that you skew the kind of traditional picture of how memory is going to be laid out. And it can lead to extremely long garbage collection pauses. There's a Hadoop distributed file system that's JVM based, and the longest garbage collection pause I've ever heard of was 10 hours when a Hadoop file system, I think it was at Facebook, basically went nuts and spent 10 hours trying to collect garbage. So this is really bad, obviously. If you're really interested in what's possible to tune Spark, there's a great blog post on the Databricks website, and I just included a few of the options. It was actually written by some guys from Intel that discussed what they recommended for tuning. I have to say, for those of you taking photos of the slide, this is actually going to be obsolete because of the re-engineering they're doing inside Spark. But nevertheless, it's a great article for understanding like how to do profiling of the garbage collector, if you really want to read it. The other problem, though, that's sort of related is really the way the Java object model works. The model is extremely flexible, and it's worked really well for the general case of building stuff, but it just kind of breaks down when we get to big data, where I have, like, say, billions of the same thing over and over and over again, just records. And it's kind of inefficient, too. So you might see a string like this, and this is an example I took from a Databricks talk about this subject. ABCD, the minimum storage, if I just assume UTF-8, is going to be 4 bytes, right? But in fact, it's 48 bytes in the Java object model, and that includes a 12-byte header that every object carries, 8 bytes for the hash code, because they always compute the hash code for an object so that it's ready in case you need it, which you may never need it if you have trillions of these things. 20 bytes of overhead for the array itself that's actually holding this data, and then 8 bytes for each of the characters, which are actually UTF-16. So not terribly efficient. Again, not so much of a big deal if I have maybe thousands of strings, but if I'm up in the billions of strings, then it really makes a big difference. The other problem, though, is the way memory is laid out. Again, this is great for flexibility in the general case, but really bad for the specific case of records where I'd like things contiguous. Each of these lines here is a cache miss. So if I'm trying to read this data into my CPU to do some sort of whatever over it, I'm going to probably miss, not find like third and zeroth and so forth in the cache, and I'll have to go out to memory again. So it's terribly inefficient to have data spread out like this, again, over millions of occurrences. And here's an example for just an arbitrary object, that, like a person type, that where maybe I can inline the age of the person because that's a primitive, but I've got yet another reference off in the heap somewhere for the name. The address is yet another object with its own references and so forth. Again, nice for flexibility, but really bad when I've got billions of them. And even hash maps are a problem. Even though they're a very useful data structure, each hash bucket is once again a linked list of stuff, so I've got just lots of lines. Okay, and we're going to come back to the solution in a minute. I'm just setting up some of the problems. One of the things they discovered through experimentation was that Spark jobs tend to be CPU bound. And this is actually also something that's new. The previous MapReduce API tended to be I/O bound. But for doing various experimental and analytical studies of this, some people at Berkeley, University of Berkeley, discovered that in general, improving network I/O, you can only expect a few percentage points improvement. Disk I/O, which is also a well-known bottleneck, actually wasn't that significant. In other words, fixing those problems is not going to give you orders of magnitude improvement, right? So obviously you need to know what problem you should optimize to fix if you really want to get dramatic improvements. So it means we need to do something about what's happening in the CPU when we're actually processing stuff. Well, it's worth maybe taking a step to the side a little bit and asking, all right, well, why is this flipped? Why have we gone from I/O bound to CPU bound? And a lot of it reflects the evolution of hardware since 2000 or so, when MapReduce ruled the land. We have extremely fast networks now, and the networks are actually faster than old spinning hard drives in a lot of cases as far as throughput, if you don't have a lot of contention or whatever, depending on how you structure the network. And of course, solid-state drives are noticeably faster too. So we've reduced I/O, or we've improved I/O performance, but we've also gotten smarter about how we use it. So for example, I mentioned that Parquet format. One of the things that you can do with Parquet is do predicate pushdown. So if I'm doing a query where I only want to see a range of records, I can actually have the Parquet driver only return to me the stuff that fits within that range and not return everything that I'll then just turn around and throw away. We also cache stuff in memory more effectively, so there's less round tripping to hard drives. That was a big problem in MapReduce. And I guess I just mentioned Parquet and how it, so one of the other ways Parquet improves performance is by storing by column. If I have, say, hundreds of columns in a record, but I'm only asking for 5, I'm only going to read the disk blocks for those 5 columns and not just read in all of the records and then throw away most of the data. And similarly, the columns are compressed by default, so that'll also optimize I/O. Okay, and we're actually, all of this is forcing more computation on the CPU too to shift the balance, like using serialization more often to get stuff around the cluster, using compression more often and decompression, of course, and then doing a lot more stuff with joins and group bys as opposed to pre-aggregating data so that we end up doing a lot more calculations of hash codes. So we're going to have to fix the CPU, and that mostly means improving algorithms and improving the use of memory. So obviously you can, they always say, pick the best algorithm and not just be too naive about it. But it turns out in modern architectures, memory utilization and especially optimizing cache performance is really crucial. So that created this, or led to the creation of this project called Tungsten, which was an initiative over several releases of Spark to improve the performance, again, at the data frame SQL level, where it's a more constrained problem, as opposed to the RDD API, which is now seen more as kind of like an assembly language for Spark, if you will. So the goals were these. I don't know why that disappeared. Anyway. First, we want to reduce the number of references. So we want to get rid of as many of these lines as we can so we get better cache performance. And we also want to improve how we lay out stuff so that we get rid of some of that overhead we discussed that we don't really want, like an array that takes 48 instead of 4 bytes. And if we do that, if we combine some of these objects in some way into bigger chunks, then that means we have fewer objects to manage by the garbage collector, and they're just bigger. So deleting one object will accomplish a lot more. And once again, if everything is contiguous, then we'll probably have it, or at least be more likely to have it in the cache line that the CPU has already loaded when we're trying to process it. And the other thing we want to do is eliminate the overhead of evaluating an expression. So for example, I write this SQL query where I'm going to, in this contrived example, I'm going to add 2, let's say, integer fields together. The naive way of doing this would be parse this SQL query and then have some built-in operators that are maybe, like using a class hierarchy with virtual functions and so forth to actually evaluate the expression. But once again, do this billions of times, and that all this sort of overhead that I've listed here becomes a noticeable penalty. So can we actually eliminate this kind of stuff? And the secret will be to actually generate custom bytecode. So let's look at what they actually did. And it's mostly finished now. The last steps that I know of are coming out this summer. One is they introduced a new encoding for objects. This is kind of cool, actually. The type is called compact row if you look in the Spark source code. But instead of having all of these references around and keeping things like hash codes and stuff that we don't really need most of the time, it starts off with a bit field that represents whether the value is null. And if a value happens to be null, and implicit here is that I know what the schema is of this data. If the value is null, then there won't be anything about it in the rest of the object. But if it's not null, then I've got these 8 bytes per values, organized by how the fields are laid out. If it's something like a long, where I can inline it, then it's just the values inlined in this values section. But if it's not, if it's, say, a string or something, then it's that 8 bytes will be a pointer into the variable length section of the array at the end. So again, this is like a byte array, and they're just putting this stuff in line when they can. It's all going to hopefully fit in a cache line, or at least most of it will. And the other cool thing about computing hash code and equals is I can just rip through the bytes. I don't have to do any fancy computation for those. I just rip through the bytes, and I can tell, maybe by the 5th bit, that these are not equal, and the hash code is very fast to calculate too. So those things are also sped up. So if you compare what we had before with something we have now, then we're going to have much better cache performance, actually much more efficient storage, and not carrying a lot of stuff like a hash code value that we don't really need. They also introduced a custom implementation for maps that basically use basically hash maps, where they're just going to have this one single page of memory where they basically line up the key value pairs sequentially, so that once again I have one big object I'm managing, not a bunch of little linked list kind of things. And that gives us this better in-memory layout, cache performance, the whole bit. And then finally they're using sun, miss, unsafe, the infamous API that basically gives you malloc and free, if you've ever done C programming, so that we can do some of these allocations off heap when that seems to be the smart thing to do. And they don't always do this, but there are cases where it's actually better to just reserve the heap for more general purpose things and just have big pages of memory that are managed themselves. The last one is this expression overhead. So what they've done up to this point is they've generate custom bytecode for sub-expressions and queries like so. And in 2.0, which is coming out this summer, they're actually going to generate bytecode for the whole query. And it turns out they're seeing like an order of magnitude improvement in performance over big queries by generating bytecode for the whole thing. So it's kind of dramatic. And this is a great example to me, maybe in the extreme of an abstraction versus the implementation. If you have a narrow, well-defined abstraction that hopefully isn't too leaky, then it gives you a lot of room to do optimizations under the hood, including completely bypassing Scala, Java, the JVM, and doing something really extremely customized. Okay, so a few other things that are kind of annoying missing features in Java. One is that we don't have value types, although that is possibly going to come in a future release of Java. Now, this is something we already know from Scala because we have a limited form of this now, where if, and I came up with an example, like suppose I have timestamp objects and I want nice methods for like doing arithmetic on timestamps, but all I really have as far as state is like a single field that happens to be a primitive. Well, it's kind of stupid to encode a class that I heap allocate and all this stuff, when in the bytecode, all I really need to do is keep that single primitive that I could push on the stack and not heap allocate. So we've got this in Scala. Like I say, if you have case class extend any val, then you'll get that optimization. But we'd really like this to happen automatically at the JVM level. Another thing that maybe a lot of you don't know is that long operations aren't actually atomic in the JVM spec. So it's possible you could get basically synchronization errors from doing long arithmetic. So you have to be careful about this. A rather annoying thing for data is we don't have unsigned types. So there's no way in our great type system to enforce that this is illegal. And we have to just do a check that we're not trying to do factorial of -1. And that has another implication, which is that arrays are indexed by integers, which means, and because we don't have unsigned integers, we can only have 2 billion elements in an array. And if it's a byte array, like we're using for serializing objects to send over the network, then we're limited to 2 gigabytes. Once again, in a world where we're getting into terabyte size RAM and corresponding heaps. This actually turns out to be a huge problem. And I want to show you an example that kind of illustrates what's going on here. So this is a real Spark shell session, and when you start the Spark REPL, if you're not using a notebook, it really is just the Scala REPL if you're using Scala versus Python, let's say. So I'm going to declare a number that represents 1.1 billion, and then I'm going to fill up an array with that many elements. This will be an array of shorts. There's this nice little, actually, do I have a build here? Let's see. Oh, okay, I guess I don't. There's a nice little utility in Spark where I can estimate the size of the array. So I'm using that to figure out what I would expect, that it's about 2.2 gigabytes in size. Now, if you have, say, reference data that you want all of your partitions to be able to see, like I'm going to do some sort of lookup against that reference data, but I don't want to treat it as an RDD itself, there's this notion of a broadcast variable where I could pull that in memory and then broadcast it around the cluster and then use it as in this example at the bottom that I'll get to here in a second. So that's what I'm going to do here. I'm going to take that array I just declared and broadcast it around my cluster. Now, I put in this estimate of B to emphasize the point that B, this broadcast variable, is a reference to something huge, but B itself is tiny, okay? So there's, what's happening here now in this final line is I'm going to take integers from 0 up to, but not including 100,000, parallelize, turns them into an RDD, although it's almost a trivial point. And then I'm going to do something silly, really, or trivial anyway, which I'm going to map over all those indices and get the value of my broadcast variable, and then get the ith element out of it, and for what it's worth. It turns out that this will be a giant array of zeros. If you recall, I created the array and just put zeros in there, so it's an extremely trivial example. But it illustrates what goes wrong. A couple things to know if you don't know this about Spark. But in my REPL here, it's actually running the parallelize method, and it's calling the map method, but that's returning this sort of abstract object that represents that node in the data flow, but nothing's actually running on the cluster yet until I say go. But this anonymous function has to be serializable because that I'm going to send over the cluster when I actually run this map step. So this has to be a serializable object, and this trips up Spark users all the time. They'll inappropriately capture something that isn't serializable. Well, what do you think should happen here? Well, B is small, and it's just a little reference thing, so it ought to be okay, and it's not big in any way. But when I actually run this is what happens. It goes boom, and it throws an exception, out of memory error. Requested array size exceeds VM limit. That basically means I tried to allocate an array bigger than 2 gigabytes. But it begs the question, where's the array? Well, actually, I lied to you. It's not actually that byte array that's the problem. It's actually the REPL itself that's the problem. Because it turns out Spark actually does handle very big broadcast arrays. I have some customers in New York that routinely load like 40 gigabytes of data into the REPL and then broadcast it around the cluster, and that actually works fine. Because Spark internally will break it up into small arrays and then reassemble on the other side. It's annoying they have to do that, but they do handle that. It's actually a problem in the Scala REPL. So if we look at the stack trace, and I pulled out a few of the interesting bits here, it was thrown when I called that map method, and I hadn't actually, I said that it's a lazy thing, right? So this happened immediately when I called the map method, not when I tried to actually run the job. So there's this method under here that tries to tell if things are serializable, and what it does is it actually serializes the object and then catches the exception if it fails. But if we drill into what's actually happening, yes, it is actually failing as it tries to serialize a byte array, but the question is, why is it copying an array? I said there's no array in that anonymous function. It was just that little reference to a broadcast variable. So where's the fucking array coming from, pardon my French? There is no array in this expression. It turns out it is this array that we started off with in the REPL, even though I'm not trying to use it directly. I'm accessing it through the broadcast variable, which means that it'll, on the other side of my cluster, it will pull it out of memory, but it won't try to just serialize it now and throw it over there, or at least that's what I thought was happening. But in fact, that is what's happening, and here's why. So when you write code like this, and here I've compressed it so that we can see it all in one space, what the Scala compiler actually does in order to satisfy the requirements of the JVM is it wraps each of those lines in a synthesized class. And then it nests them. If you've ever looked at what's dumped from a long session, you'll have this huge nesting of these objects that are wrapping all the previous expressions. So when I do this, I'm closing over B in this closure now. And B is now a field inside this outer class. Of course, I left out a lot of details. But because B is a field, now it sucks in the entire instance of the class, and that happens to include the original array. And that's why it's not serializable, because I really did try to serialize the whole array. This just confuses the hell out of new people to Scala and to Spark. And it's something that we should not have. So we're actually investigating whether we can fix this, re-engineer the REPL to be better for these big data scenarios. You know, you could say this is a bug in the REPL, but really it's actually pushing the REPL beyond what it was originally designed for. I don't think Martin ever thought people would try to put like 40 gigabyte arrays in the REPL, and why would you, right? So just quickly, there are some, how are we doing for time? Pretty good. There are some workarounds, and I'll just briefly mention what they are, and then we'll be done. One is if you declare this transient in the usual way, that avoids serializing over something if it's marked as transient. But you know, it's weird to do this in the REPL, right? The other thing you can do is the old trick of just encapsulating stuff like data, in this case, inside a separate object so that the data object, and then do this trick too. You have to declare a variable that grabs the get B in this case. And then you won't serialize over the data object. You'll just serialize over the work object in this case. And that way, we won't serialize the array. Once again, once you learn this stuff, it works fine, but it's kind of not very unintuitive. So this is what we have to do. And that's pretty much it. So some conclusions. Scala is actually, adoption is being driven a lot by Spark right now. But I think it's actually moving too fast. The project is accumulating a lot of technical debt, in my opinion, and I'm a little worried that eventually it'll catch up to it, but we'll see. I'd also like to see some of the stuff that Spark introduced work its way back into Scala collections, like some of these convenience methods for working with key value pairs. And I just grabbed a list of some of them here that are pretty nice. Maybe we should work some of these Tungsten optimizations back into the Spark collections. You know, it may not make sense. You always have to be careful. Like the Scala parallel collections actually didn't turn out to be that good or that useful because the overhead of parallelization often overwhelmed the advantages of it. So you'd have to be careful that this is actually a benefit. But it would be nice if maybe we could get at least the object encoding as an option for maybe at the JVM level. You know, that linear encoding for better cache line performance and stuff. And I would love to see some of these other things fixed that I mentioned, like be able to index arrays by longs, get real true value types, and true unsigned types. But those are maybe less crucial. Once again, you can get this talk at my vanity website, polyglotprogramming.com. And I've got a white paper, if you like reading white papers from vendors, that goes into our view of fast data a little bit more, and then that's it. So thank you very much. I think we've got 2 minutes for questions. If there's one over here.
In the beginning of your talk, you mentioned there are 3 representations of data set in Spark, RDD, data frame, and streaming. And then you mentioned the graph library and the machine learning library. So does those library take all 3 representations like as input?
Yeah, that's a really good question. So it's actually a problem that they don't right now. So for example, if you're working with streaming, it would really be nice if streams are oriented around data frames. But what typically happens is, and I'm talking about what's happening as of before 2.0, this is actually all changing over the next 6 months in Spark. But in a streaming case, you'd have to pull your data in as an RDD and then parse it with like the Parquet parser and data frames and so forth. So it's not well integrated, the ability to use data frames versus skipping RDDs when you're working with these other libraries. And in fact, all of them are changing. The ML library is being replaced effectively by a data frame-based library called ML for confusion. And then the GraphX library is a bit orphaned at the moment, but there's a new one called Graph Frames that's based on data frames that will probably become the true graph library. So they are moving in that direction, but right now it's a bit awkward to use data frames with these higher level APIs. Is there anybody else? Up front here. Wait for the mic there if you don't mind.
Is there any of these optimizations something that could be interesting of coming into Scala as, or even JVM? You mentioned it a little bit that you will have wishes to the JVM. Do you have contacts there?
Yeah, I don't know any reason why you wouldn't want to do this unless for some reason the performance actually wasn't enough benefit to justify all the extra engineering you had to do. But I'd like to believe that making the Scala collections use some of these optimizations would make them much faster. But I think the problems that I'd really like to fix first would be like the REPL and things like that. I think I saw another hand, or maybe it was scratching. All right, well, thanks very much.